A 5-gallon bucket sits on a cinder block in the corner of a garage. Cloudy, silty water goes in the top. Clear water drips out the bottom, slow and steady, into a jug. No pump, no power cord, no cartridge to replace every 3 months. Just sand, gravel, and a container, built once and left alone. For the first several days after you build this thing, you're going to run water through it and throw that water away. That's not a mistake. That's the entire point, and by the end of this video you'll know exactly why. What you're building is a slow sand filter, but the working part of it isn't the sand. It's a living layer called the schmutzdecke, German for dirt skin. It's biology doing the job people assume only chemistry or pressure can do. By the end of this video, you'll understand how that living layer forms, how to size the container, and where your local plumbing code draws a hard line. Most people's first instinct is to treat a sand filter like a coffee filter. Pour dirty water in, get clean water out immediately. So they build it, run water through on day 1, drink it, and either get lucky or get sick. People assume sand filter means purely physical strainer, so they pack the sand as tight as possible and expect finer sand to mean cleaner water. Tighter packing and finer grain size mostly just mean the filter clogs faster and flows slower. It doesn't replace the part of the system that actually removes pathogens. The just buy a countertop filter path. Those systems work by physically forcing water through a very fine physical barrier under pressure, replaced on a schedule. That's a completely different mechanism doing a similar looking job. Swapping one assumption for the other is how people either waste a good filter or trust a bad one. Raw water goes in first, poured over a diffuser plate, a simple flat plate with holes that spreads the incoming water gently across the surface. Below that sits a shallow layer of standing water that stays there between uses. That layer is what keeps everything below it alive. Under the standing water is the sand bed itself, and the top few centimeters of that sand bed is where the schmutzdecke lives. Below the sand, a layer of coarser gravel acts as a transition, stopping fine sand grains from washing down and out. At the very bottom, a bed of gravel wraps a perforated outlet pipe, which carries filtered water out of the container and into your collection vessel. Water moves down through that whole stack under gravity alone. No pump, no pressure, just the weight of the water above pushing it through. One-sentence version: dirty water sits, gets eaten from above and strained from below, and only what survives both gets to leave. Everything in this build hangs off one relationship. Flow through a packed bed is driven by pressure and permeability, not brute force. The pressure drop across a bed of packed material is proportional to how fast the fluid moves through it, divided by how permeable that material is. Deeper media means a bigger pressure drop. Pause, a given flow rate through a given cross-section needs a matching amount of head pressure pushing it. You cannot make a filter flow faster for free. Push more water through the same footprint, and you need more height of standing water above it, or you get less flow, not more. You cannot make a filter safer just by using finer sand. Finer sand raises resistance and slows flow, but the thing actually neutralizing pathogens is the biological layer sitting on top. Think of it like a single revolving door at a crowded building entrance. Make the door narrower and people move through slower. That's the sand. Whether the people getting through are actually supposed to be there is the security guard standing next to the door. The guard is the schmutzdecke. Grain size controls the speed. The living layer controls what actually gets through. Filter media is the one place cutting corners costs you the whole build. You want clean, washed sand and gravel, free of clay, silt, and organic debris. Damp sand runs in the neighborhood of 1,200 to 1,360 kilograms per cubic meter. Dry sand closer to 1,440 to 1,600 kilograms per cubic meter. A loaded filter is not something you casually move. The container itself needs to be built from an approved, durable, non-absorbent, corrosion-resistant material. Anything touching that water, coatings, liners, fittings, should be rated for potable contact, not just food-grade adjacent. Never line or patch the inside with anything that changes the taste, odor, or color of the water. The diffuser plate and outlet pipe don't need to be exotic. The requirement is that they're rated for contact with drinking water and sized to spread flow gently rather than concentrate it. Bedding material should be clean and sized to pass through roughly a half-inch screen. Skip anything sharp, angular, or cinder-based. Prices for sand, gravel, and containers vary enormously by region. Check a local landscaping supplier or hardware store, rather than assuming a number from the internet. Size this filter to your actual household water use, not a guess. Start with per-person daily demand. A household using efficient, water-conserving fixtures runs somewhere around 60 to 118 liters per person per day. A household without conservation habits can run past 378 liters per person per day. Scenario 1. Small and conservation-minded. One person, efficient fixtures. That's a small filter, sized for occasional top-offs rather than continuous flow. Scenario 2. Typical household, a family of 4. You land somewhere around 240 to about 470 liters a day. That's the range most home-built Biosand filters actually need to plan around. Scenario 3. Heavy use. A family of 4 without water-conserving fixtures. You're over 1,500 liters a day. That is not a number a single household Biosand filter is meant to carry alone. Pause. At that volume, you're looking at either multiple filters running in parallel or treating this build as a supplement to your main supply, not a replacement for it. The safety margin doesn't come from oversizing the container to some enormous size. Remember, more cross-sectional area means more standing water needed to maintain the same flow. A container that's mostly empty, most of the time just gives that standing water layer more opportunity to sit stagnant. The margin comes from sizing to your typical, realistic daily draw, and treating anything past that as a sign you need a second filter, not a bigger one. Phase 1. Prepare and sanitize the container before anything goes into it. Whatever holds your water needs to be flushed clean, then treated with a chlorine solution. Pause. Either at least 50 parts per million held for 24 hours, or at least 200 parts per million held for 3 hours, then flushed again with clean water until no trace of chlorine remains. Phase 2. Install the outlet pipe and base gravel layer first, before anything else goes in. This order matters. Install sand first, and you have no clean way to set the underdrain. Phase 3. Build the gravel transition layer above the base, sized to keep sand from migrating down and clogging your outlet over time. Phase 4. Add the sand bed itself, using clean washed sand, and let it settle before you go further. This is your main filtration depth and the future home of your schmutzdecke. Phase 5. Install the diffuser plate above the sand surface. This is the step people skip because it looks unnecessary. Pour water directly onto bare sand without a diffuser, and you carve a channel straight down through your media, and water finds that channel every time afterward. Phase 6. The pause. Run water through. Let the standing layer establish, and then leave it alone. This is where the schmutzdecke actually forms, a living community establishing itself on the sand surface, and it needs quiet, undisturbed time to do that. Every day you skip, or every time you scoop into that top layer out of impatience, sets the biology back to day 1. Phase 6 completion. The pause period concludes with a settled, functioning filter. Transition into the deobelier modes. But even a correctly built filter can fail if it isn't maintained. Failure 1. The dry out. Symptom. Your filter suddenly performs like plain sand, no better. Cause. The standing water layer above the sand fully drained and stayed empty for too long. The living layer that depends on that water starved. Fix. Rebuild the pause period from scratch and never let that reservoir sit fully dry again. Ignore it, and you're drinking the output of a strainer, not a purifier. Failure 2. The stirred bed. Symptom. A sudden spike in cloudiness right after you touch the filter. Cause. Pouring water in too fast without a diffuser, or cleaning the filter by digging into the sand surface instead of gently skimming it. Either one tears open the schmutzdecke. Fix. Always pour through the diffuser, and if the top layer ever needs maintenance, skim, never dig. Failure 3. The stagnant trap. Symptom. Water that came out clean gets contaminated again before anyone drinks it. Cause. Standing water sitting warm, in the range of roughly 55 to 133 degrees Fahrenheit, is flagged as prime territory for hazardous bacteria to multiply inside an open or uncovered collection container. The filter did its job. Storage undid it. Fix. A covered, potable rated collection container, and don't let filtered water sit around in warm conditions for long stretches before use. Transition into the code and safety. Beyond the biology and the build, there's a legal line this project runs into. A filtration device connected to your household water supply isn't just a workbench project, it's regulated. Under the International Plumbing Code, a water treatment or conditioning device is defined as anything that changes a water supply's chemical content or removes suspended solids by filtration. Code requires the piping connecting it to be sized and built to manufacturer specifications, meeting applicable NSF standards for potable contact. Pause. Code requires filters and treatment devices to be designed and located so outside contaminants can't get in, and any overflow, relief, or waste discharge has to terminate through an air gap, never a direct connection to a drain. Installing a filtration system tied into your household plumbing generally requires a permit. It does not qualify as exempt minor repair work, and permitted work gets inspected while it's still visible, including pressure testing. If your source water is a private well or surface source rather than municipal supply, your local health authority needs to test and approve it as potable before it's connected to your household plumbing at all. This filter does not replace that approval. This video is educational and not professional electrical plumbing or structural advice. Codes vary by location and change over time. Mains voltage can kill, and stored water and stored energy can both destroy property. Have your plan checked by a licensed professional and your local code office before you build. On screen simultaneously, educational only, and ZISI against your local code. Transition. With the legal and safety line drawn clearly, the video closes on what this build actually costs and what it enables next. The materials here, a container, sand, and gravel, cost a small fraction of what you'd spend on a commercial multi-stage or UV system. You're buying inert material once instead of replacement cartridges on a recurring schedule. The honest payback statement is patience, not just money. Note, repeat on screen, educational only. Verify against your local code. This build pairs naturally with a rainwater catchment system feeding it. Clean, gravity-fed source water in, purified water out, no grid and no pump anywhere in the chain. Build it once. Understand it forever. Subscribe if you want the rest of your homestead explained the same way.